energetic students. Now, some of you are preparing for NSEP exam, some for JEE exam, some for NEET exam, and some of you are not even preparing for any exam and you're just physics enthusiasts. And that's what brings you here to my classes. So today we are going to talk about the Boltzmann constant. See, before we start today's session, I just want to share my disappointment that some students take constants as just numbers. I mean, for them, it's just a number. उसकी वैल्यू एग्जाम में दी होगी, इस फॉर्मूला में यूज हो जाएगी, end of it. You really have to go in depth, and you should be understanding what does a constant actually signify. Is there a real life meaning to that? Is there a reason like this value, this constant has this value? And is it a fundamental constant, or is what is it? I mean, you really have to honor these constants, especially like Boltzmann constant. I'm not going to talk much here because it's going to be very boring here. Let's dive into the subject here. So my name is Bhavdeep Sethi. Very quick introduction. I did M.Tech from IIT Bombay, and I have been converting physics haters to physics lovers. And with due respect to all the awesome books out there, I proudly say that beyond those books is the nature. Nature is the best textbook in physics. Explore nature and you know physics. Now, again, as with all my sessions, there is no spoon feeding. You're not going to get any ready-made content here to memorize and pass your exam or clear that competitive exam. It's more about the concepts here. So there's no spoon feeding. We are going to go in depth conceptually. Okay, so to start with, what is Boltzmann constant? The value is this much. I mean, obviously, you don't have to memorize this value. Any exam will give you this value. So if you're just looking for the value here, that's the end of the session for you, because this value anyways you don't have to memorize. It's going to be given in your exam. Wherever you have to use Boltzmann constant, just take that value. But to honor the person, at least know that it's named after a great personality out there. Now, understanding this constant gives you insights into a lot of things. So first of all, what is this constant trying to do? It is actually bridging the gap between the micro and the macro world. What do I mean by that? So let's understand with a very simple example here. So experimentally, we know the product of pressure and volume is going to be proportional to the temperature, and it's all common sense. I have taken other sessions on that. More the pressure or more the velocity of the molecules, more the collision, and more the impact of those collisions on the wall, so more the pressure. So temperature and pressure are directly proportional, and we have spoken about that many times. But in short, if I can say pressure times volume, so this value is directly proportional to the temperature, because as temperature, what is temperature? Temperature is a measure of the internal kinetic energy of those molecules. More that kinetic energy, more the pressure and all that. So this we know. I mean, this is something we know experimentally. So if you have to remove this proportionality and bring in some constant out there to make it an equality, you would write PV is equal to some constant that let's say we don't know that. Let's say there is some constant times the temperature. So that's coming from experiments. Now, if you just sit down on the table and give a thought about it, what would that value depend on? So given a particular temperature, what will this product depend on? Wouldn't it depend on how much gas it is? Because think about it, at 20 degrees Celsius, if I take a container and put 4 molecules versus 10 molecules, those 10 molecules are going to have more impact on the wall, making it more pressure. Right, now I'm talking about microscopic, but we can't see microscopic things. So let's talk about the grams maybe. So let's take a container and put in 1 grams of gas in there. So at 20 degrees Celsius, there is a certain momentum they have, certain kinetic energy on an average they have. So they will impart some momentum on the wall, creating some pressure. If I double the gas to 2 grams, it's going to be more pressure. So can I say this something with amount of gas has to come in there? Now we measure amount of gas in moles, right? So we say, okay, it's about number of moles, and also it's directly moles. So there has to be some constant here, and I'll create another video on that, and that constant comes out to be the gas constant. It doesn't depend. So this is a universal gas constant, sorry, and then it depends on how many moles of gas it is. It might sound surprising at first look, like why does it not depend on what kind of gas it is? And again, it's coming down to the concept of the Avogadro's number, where we are saying any gas, one mole has a fixed amount of number of molecules, right? So some other video on that. But for now, we understand this is the ideal gas equation. Now, if you think about it, this is pressure, volume, and temperature. These are macroscopic properties. So we can measure the pressure, volume, and temperature. We can feel it. These are macroscopic world. But what if I want to go in depth and see at the molecular level? So instead of the number of moles here, as I was speaking earlier, we have to plug in the number of molecules there. So what is Avogadro's number? Avogadro's number is the number of molecules in 1 mole of gas. 1 mole of gas will always have these many molecules. So 2 moles of gas will have this times these many molecules. 3 moles will have 3 times of this molecules. So if given a number of molecules here, I want to find how many moles it is. Those number of molecules divided by the Avogadro's number will give me the moles, right? As simple as that. Every mole has these many molecules. Given a number of molecules here, I can divide by this number. I will get how many moles it is. So if I want to go to microscopic world, and I want to say, no, I don't like the number of moles here, I want to put something, the number of molecules, I can convert this equation to say PV is equal to N, which is N is the number of molecules, the total number of molecules divided by Avogadro's number. So this is the number of moles. So I'm just replacing lowercase n with this. It's the same thing, times this gas constant times the temperature. This is a constant, this is a constant, and this is where the Boltzmann constant comes into play. And then we say, okay, let's make this a new constant, and let's call this a new constant, which is the Boltzmann constant. So Boltzmann constant is simply when you are going into the microscopic world. So you can rewrite this gas equation as PV is equal to N times the Boltzmann constant times temperature. So Boltzmann constant is basically bridging our gap between converting, see this is macroscopic properties. These are macroscopic properties. This is a macroscopic property. This is a microscopic property. So when you want to go from the macroscopic world to microscopic world, you actually bring in the Boltzmann constant. And I'm going to talk more about it in upcoming videos, because this constant is actually a fundamental constant. So in the ideal gas law, you can clearly see macroscopic, macroscopic, microscopic, macroscopic. It is bridging the gap. Something that you can measure, something that you can't even see. Talk about entropy. Now, entropy, what is entropy? It's a measure of the disorder. Right. So taking a simple example here, let's say, and a classical example, I'm going to take the same example so that you can understand more. So let us say there is a container here. So there's a container, let's say there's a container here, and let's say there are 2 molecules in there. So let's call this, or let's take 4 molecules. So let's take 4 molecules as in yellow molecule, then there is a green molecule, then there is a blue molecule, and maybe a white molecule. So there are 4 molecules. How many possible ways can you have these 4 molecules in this container? Just one possible way. I'm not saying east, west, north, south. I'm just saying what are the different possibilities that it can have. So let me take another example, then you'll understand what I'm talking about. So let's say I change this configuration and I make an opening here, and I have another container here. So this thing, I just put an opening here and I connect to another one. So how many different ways can the molecules rearrange themselves between these 2 containers? All 4 can be here, all 4 can be here, 3 can be here, 1 can be here, or 3, 1 here, or 2, 2. Now if you think about it, If I'm saying 2 2, 2 2 can be red here, sorry, yellow and white here, or maybe blue and white here. So all these are different combinations. So that is now bringing in more disorder, as in there are different micro states. So what is a micro state? What are the different states that it can reside in? There was only one state it can be in here. All four will have to be here. But now one can be here, three can be here, three can be here, one can be here. These are called the micro states. This is called the disorder in the system. Now entropy is a measure of disorder. No, but see, entropy is something macroscopic, something you measure. But these disorder are micro level. These molecules, it can be more like, let's say, white here and other three here, or maybe red here, so green here and the other three here, blue here, other three here. These are different micro states. So how do I connect this micro state, which is a microscopic property, to entropy, which is macroscopic property? Again, Boltzmann constant comes into play. We are saying entropy is equal to the Boltzmann constant times the log of this disorder. Disorder is the number of micro states. So here you will plug in one. Here you will plug in all the different 16 combinations possible here. So you'll plug in 16 here. Because if you think about it, all four here, one combination, all four here, second combination, three here, one here, but that three here, one here will have different variations. Maybe white is here, maybe blue is here, maybe green is here, maybe yellow is here. So four different combinations here. Similarly, one here has four different combinations. Similarly, two here will have yellow and white can be here, green and blue can be here. So all those combined together will give you 16 permutations or combinations actually. So 16 will plug in here. So see how the Boltzmann constant is bridging the gap between something microscopic to something macroscopic. Let's look at more examples here. Temperature and energy. Now what is temperature? Temperature is a measure of internal energy of the molecules. Internal energy, half mv squared. Oh, there's a molecule here, half mv square. There's a molecule here, half mv square. Molecule here, half mv square. But all these molecules have different speeds. They have different kinetic energy. So when we take in the average, it is some joules out there, right? A very tiny number that our brain cannot digest. Our brain does not understand very small numbers. Our brain does not understand very big numbers. Our brain understands some numbers that we can count 1, 2, 3, 8.9, 16.52, something like this. So if I'm talking about those energies, those are so small, I'm not able to understand that. And this is where the temperature comes in play. Temperature converts those microscopic properties to something macroscopic that I can understand. So how does that work? Again, we have made a lot of videos on this. So temperature is a measure of kinetic energy. So basically it's more about 1 by 2 kb. Sorry, what I'm trying to do. So let's write it the other way. So the average energy of a molecule, again it's average energy, remember, because energy of each molecule is different. That is going to be 1 by 2 Boltzmann constant times the temperature per degree of freedom. Degree of freedom is how many different states you need to describe that molecule. If it is monoatomic, it can travel in x along x-axis, y-axis, or z-axis. There are three degrees of freedom. So for a monoatomic gas, so this is per degree of freedom. So if you're talking about the monoatomic gas, you will say the monoatomic gas energy per molecule is 3 by 2 Boltzmann constant times the temperature. Now think about it. This is a macroscopic property and this is microscopic property. Isn't it bridging the gap between those two? I will not be able to understand if somebody says, oh, on an average, the molecules have 2 times 10 to the power negative 23 joules. I mean, I'm not able to compare or grasp that information. But if I'm told, okay, the temperature of the gas is 20 Celsius or 293 Kelvin, that's something I understand. That's macroscopic quantity. So macroscopic, microscopic, and this is exactly what the Boltzmann constant is trying to do here. Heat capacity. Now coming back to this, so what is heat capacity? Heat capacity is given a unit amount of substance, how much heat would you provide to raise the temperature by 1 unit? Again, if you have a unit mass, how much energy you need to raise the temperature by 1 unit? Maybe 1 kilogram, 1 Kelvin, 1 gram, 1 Celsius. I mean, it's completely up to you what systems of measurements you want to use. But 1 unit of mass, increase temperature by 1 unit, how much energy would you need? So if I talk about one molecule, let's say, so one molecule on an average has how much energy? One molecule on an average has, for monoatomic gas, let's say, it has 3 by 2. Remember, it was half kBT per degree of freedom, but monoatomic molecule has 3 degrees of freedom. So 3 by 2 kBT. So that is the energy that this has, right? So this is the per molecule energy. So what is specific heat? Specific heat is the energy required to change per unit temperature. So wouldn't the specific heat be equal to the rate of change of that energy with respect to the temperature? Because when you change the temperature by a unit, how much energy changes, and that energy is required to be pumped in. So if you do the derivative of this, what you end up getting is 3 by 2 kb. So see how the specific heat per molecule is 3 by 2 kb. But I'm not interested in the specific heat of a molecule. I'm interested in the specific heat of some bulk mass out there. Maybe the gas inside this room, or maybe 1 mole of gas. So 1 mole looks more meaningful because per unit mass. So let that unit be molecule, that unit be mole, right? So if I want, I know this is the energy requirement for one molecule, but for how much will be the energy requirement for two molecules? Multiply this by two. Three molecules, multiply by three. 1 mole. 1 mole has Avogadro's number of molecules. So per mole, so if I say per mole, how much is the energy requirement? Per mole energy requirement will be 3 by 2, this Boltzmann constant, times how many molecules in 1 mole? Oh, that's Avogadro's number. That's Avogadro's number. And this is the gas constant anyways. Remember, the gas constant is R divided by N. So basically we saw, so this Boltzmann constant is R by Na. That means the Na times Kb is actually the gas constant. And this is where you have the specific heat of per mole of a gas is 3 by 2 R. So you see how it's bridging the gap between something you can measure, something macroscopic, as in specific heat, and something that is microscopic. So this is what Boltzmann constant is. It's not just a number. It's something you really take it as a fundamental number. So you see how Boltzmann constant bridges the gap between micro and macro world. Again, the purpose of this video is not just to make you understand the Boltzmann constant. The purpose of this video is to make you motivate. It's to motivate you to learn conceptually. See, I'm not just teaching you something. I'm actually trying to motivate you to go in depth, whatever subject you're studying. It may be physics, it may be social science. Social science is so beautiful. Just try to understand conceptually. And I'm not kidding. Social science is very conceptual. Okay, if you like this video, obviously you're going to promote it by sending it to your friends. And if you want to join the enthusiastic team who is going to join the paid courses, so I'm going to start a new course on 10th of February 2025. It's for NSEP, which is going to be held in the month of November. So first module is starting on 10th of February. The classes will be Monday and Wednesday, 6 to 7 p.m. And the price here says 3,000, but it has increased to 4,000. So I think this slide is old, but not to worry. There's a discount going on. I'll show you. Even though the price has gone up to 4,000, you will still have to pay actually less than this. So if I go into more details of this, it's open for anybody in 9, 10th, 11th, 12th graders. There are 5 modules. Each module is 4,000 rupees. So 4,000 times 5 is 20,000 rupees of fee. And there is a test every alternate Sunday, assignment after every class, and you'll be part of the Telegram group where the doubt clearing will happen. If you want to join this, you don't really have to pay this 20,000. There's a link below where you click in and you get very less. Let's check. So let's go to Vedantu.com. So if you go to Vedantu.com, so this is Vedantu.com. If you go to courses, then all the way here you see Olympiad. So you click on Olympiad and you scroll up. So you go to Olympiad here, then scroll up. NSEP 2025 full course. Buy the full course. Why would you buy one module? So full course 20,000 tha. Oh my God, it's not even 13,000 now. There's a discount of 39% going on. Grab the opportunity, 12,150. So if you click on buy course, you will get for that price, or there is a link below. You can use that also and take the opportunity there. So I'm going to see you soon. And again, keep up the high Josh. Try to learn conceptually always. So these are the modules that I was talking about. So all these three modules, they cover the 11th ka portion. These cover 12th ka portion. So your entire physics is covered for JEE, NEET, NSEP, and conceptually, obviously. So again, students, I always motivate you to learn conceptually, no memorization, no ratification. Go to nature, try to learn physics with nature. Keep up the high Josh.